Okay, recording in progress. So now we're going to look at one of the more annoying topics. This is where we actually start looking at the purpose of the integral, like what it does. So the derivative found the slope of the tangent line. The integral is going to help us do area. But to see the application, we're going to actually look at sigma notation. Now, normally I'd kind of hand wave this, but you actually need sigma notation at the end of Cal 2. So we're going to get into it. But first, just the overall, like, what are we trying to do? So we have this ridiculous shape. Many ways to try to figure out the area, but we could count all the boxes. We could like draw rectangles. We know the area of rectangles, maybe some triangles in there. There's all sorts of crazy ways you can actually like figure this out. Ooh, works a lot better when your blood sugar doesn't feel like crashing and you can draw a reasonably straight line. So one of the more classic ways is what's actually called the trapezoid rule that, as far as I can tell from the notes, we're not actually going to do. But you're basically taking the function values and using those to create little shapes, and then adding the area of all of those things together. So here we have, suppose we're going to take this thing and we're going to split it into 3 rectangles. So we're going to split equally for the width. But we're kind of asking ourselves, like, what should the height of the rectangle be? Should it be the left endpoint? Or should it be the right endpoint? And there isn't a good answer to this. It is, especially when we're looking at only 3 rectangles. So, usually it's just pick one and go with it. Really, the answer depends more on the curve, if it's increasing or decreasing, if it's concave up or concave down. But most of the time, the curve is actually doing more than just one thing, so doesn't much matter. So this one, we're just gonna crunch by hand. So we have 3 rectangles of equal width. We want to find an approximation to the area between the curve and the x-axis over the interval from 4 to 8. And we're going to look at left, right, and midpoints. All right, so the distance between 4 and 8 is 4 units. Divided by 3 is 4/3. So our widths are obnoxious. That's 4/3 or about 1 1/3. So that puts it, so 16/3. I'm sorry, my hands are like extra shaky today. 24, 16 to 20/3, 6 and 2/3. So area of a rectangle is base times the height. We know all the bases, like we're specifically forcing all the widths to be the same width. And we're making that 4/3 in this case. So our area here, come on. 4/3 times on the left, we're going to use the left function value. So for the first rectangle, that's f of 4. We have f of 16/3. So as far as the picture goes, when we're doing the left, like this is the actual area we're finding. And from the picture, because this graph is strictly decreasing, this is going to be an overestimate of the area under the curve. It's going to be a little too big. This is 4/3 times 1/4. 4/3 times 3/16. 4/3 times 3/20. So we get 1/3 plus 1/4 plus 1/5. This is just a pure fluke because we're looking at the graph 1/x. Two and 15, 47/60. So we know the area between 4 and 8 under the curve is less than 47/60. If I go down here to do the same thing with the right, like here, Chris already rewrote the formula because we know the width of the rectangle and it's the same on all of them, so we may as well just factor it and write it up front. We have 4/3 times. Now we're doing the right endpoints, so we're going to use the 3 on the right. So this is f of 16/3 plus f of 20/3 plus f of 8. Can someone please crunch that up? Yeah, my brain didn't want to do it by hand. This times 16 times 5.
Why did you take the reciprocals?
Oh, because the function is 1/x. So 1/x is just reciprocal to things. We're gonna draw the picture. It's a little silly, but it does kind of help show what we're trying to do. So by taking the right endpoints, because this is a decreasing graph, all of these rectangles are smaller than the area under the curve. So we now know that the area under the curve is between 37/80ths and 47/60ths. All right, now the midpoints are like even more obnoxious because it's the halfway point between each of these numbers. It will give us a better approximation, but I'm gonna be honest, we don't use it. So let me doodle the picture. So with the midpoints, it's going to be closer. We get a little over and a little under on each of the estimates. This is also a longer section though. Let's see what all we got. Which way, which way? So looking at this graph, is this a left endpoint or a right endpoint Riemann sum? When we look at each of the rectangles, the height is the function value of the input on the left. So that's why we know it's a left, because it's like if we really zoom in, which apparently that's the max zoom. Yeah. Now looking at this particular curve, is that sum going to be too big or too small? Is it going to be less than the actual area under the curve or greater than the area under the curve? So the actual area under the curve, like I'd shade everything there. But the Riemann sum is just going to be these blue rectangles added together. Yep, so there's the little white spaces left over there. So for this graph, the left endpoint is an under approximation. But just to kind of compare and contrast, on the previous graph, the left endpoint was an over approximation. So it depends on whether the graph is increasing or decreasing. So now here they've got a right endpoint pictured. So now when we look at our rectangles, the height of the crossbar is determined by where the right function value is instead of the left one. Yep. So right endpoint and an over approximation of the area. So all of this is based on, like right now, these happen to be 4 rectangles, but these are all a finite number of rectangles and they approximate the area under the curve. But we can do better than this. This is annoying. And Chris found some very weird memes. So this is the thing we're going to use. Yep. The capital Greek letter sigma is used to indicate a sum in mathematics. Side note, if you want a repeated product, you actually use a big pi. But you won't have to probably ever use that. We really only do that in like combinatorics. It's weird. All right. So sometimes we want to add a bunch of things. So I've got the 1 + 2 + 3, that's real tedious. There are other ways I could get this calculation done. So we could do it with like a loop in computer science. But for the sigma, here is our basic formation. So the summation index, we typically use K as this number. And that's because very often we call the final index N because we're going to change that number a bunch. So we want to differentiate the two. N is typically the end point. K is typically the number that incrementally gets increased. Then the A of K here is, it's some sort of formula in terms of K. So we put our starting number at the bottom and our finishing number up top. No. Like I said, my blood sugar is kind of weird today, so it's taking me longer to process and answer. So some of the questions we're going to have to answer in sigma notation. Like basically it was writing ... and then whatever the endpoint would be got tedious when we started making n really big. Like even writing out 10 integers is like, it's a bit much. So we can do it with sigma notation instead. So if I start at 1 and I go to 10, then I look at these numbers and these numbers are just the integers. So this is just all the values that K is going to take as we increment through. It's like function notation. It's just for like sequences. We tend to use A's as the notation, so that's why I picked an A here. But it could have been F of K. It just means something in terms of K. Yeah. Sometimes. Most of the time, 0 ends up being 0. So having a sigma start at 0 or 1 is like meh. But at the end of Cal 2, you start looking at like infinite sums and infinite sequences, and a lot of them are fractions, and we can't divide by 0. So that's why we just like habitually start at 1. It's just in case the formula would have an over 0, we kind of like hedge around that.
It's not expected zero. So like between 0 and 8.
It could. Yeah, it doesn't have to start at 1. It can start at whatever number you want. And there's actually like some problems in number theory, like that's one of the things you do is you pull a couple of terms out and then just use the sigma and renumber the index. Just so you can mess around with the first few, do some things, and yeah. But in here, we're going to stick 1 to, typically we're going to write an N up there instead of a 10. So I think this problem is coming out of WebWork. They wanted you to get used to looking at sigma notation and being able to spit out what the terms would be. It doesn't want you to actually add the terms. It's just look at the sigma and figure out, like, what do we write? What would the next term be? What would the next term be? It wants you to clean up the individual terms, but not actually add anything. So here, like, there's not going to be a lot to clean up. It's 1 over k, but we start at 2. So we're going to start with 1/2. Now we index k to the next number, 3. We get 1/3. Then the next number, 1/4, plus 1/5, plus 1/6, and 6 is where we stop. So that is what we would type as the answer in WebWork for this, not whatever that ridiculous sum is. Right here, we have an exponential. We're doing the sum of the first 6 powers, or, well, 7 powers of 2. So we'll start with 2 to the 0, because our k starts at 0 here. Then 2 to the first, 2 to the second, 2 to the third. And see, this is why we have sigma notation, because writing all of this out is tedious. Now, on this particular one, I'm not sure if WebWork will take this or if they actually want us to write 1 plus 2 plus 32, 64. Yeah, they probably want the numbers written out because they don't get too big. That's why it's 2 to the k. If it was 3 to the k, they'd probably only go to like 5. 3 to the 5th is 243. It's less than 1,000. And that's the only number that would be bigger than 100. All right, and then this last one's a little weird, because we're taking the sum from k equals 1 to 6 of 1/6. So we're going to do the process, but there's nowhere to write the k value, but we still use that k index to count our terms. So I would have 1/6 plus 1/6 plus, now my k is 3, now it's 4, now it's 5, and finally it's 6. So I mean, we know looking at that 6, 6 is 1. But for the purposes of practicing sigma notation, understanding what it's wanting us to do, we'd actually type out 1/6 plus 1/6, then you copy plus 1/6, then paste it 4 times. And we celebrate copy paste in WebWork. All right. So sigma notation carries a lot of the same properties that we saw with derivatives. When there is a constant multiple, we can factor that out. If we are adding terms, we can split the sigma across sums. We can also split it across subtraction. And if convenient, we can split the sigma into 2 sigmas. So we could do something like, if this is from I equals 1 to 100, we could say, well, let's go from I equals 1 to 10, and then 10 plus 1 is 11. So we'd start I equals 11 to 100. Sometimes they use I instead of K for the index. So there's 3 formulas that show up here when we're just looking at more basic functions. So if I'm looking at just adding the first n integers, so if I want to know what the sum of 1 through 10 is, it's 10 times 11 divided by 2, so it's 55. I want to know the sum of the first n squares, 1 squared plus 2 squared, then I have this n times n plus 1 times 2n plus 1 all over 6. And if it pops up, the sum of cubes, consecutive cubes, is n squared times n plus 1 squared over 4, which strangely enough is the result from number 1 squared. So, not asking you guys to prove it. Proving this requires use of mathematical induction, which is obnoxious. So think of these more like given formulas. We know these to be true. N is our end number, so it's going from 1 to n. Yeah, that's a... My computer hates me. So this n is the same as those n's. So if we started with this, it equals this. Yeah. So the in-between is like saying this is what it's doing, but because like 1 through 10, we could sit there and add them up. It's annoying, but we could do it. But like 1 through 100, I don't want to do that by hand. Yeah. So these are all written in terms of n, and that's deliberate because then we're going to say, well, let's make n bigger and bigger and bigger. So right now we needed to have a name, so later we can do the limit as it goes to infinity. Well, this is all just to understand how sigma works. No, sigma just means add a bunch of stuff. So we were using it to approximate the areas because the areas were adding repeated rectangles. We're going to use that same idea in a minute, but we're going to say there's n rectangles. So seeing the initial examples helps, and it leads into why do we want this sigma notation? Because we do more than 3 or 4 rectangles, it's a royal pain in the butt. So if I wanted to know what 9 times k cubed was for k equals 1 to 11. So the first thing is that 9 is a constant. I can factor it out. So this is 9 times the sum from k equals 1 to 11 of k cubed. Now I can use my formula over here. So my n number is what shows up in the formula. My n number here is 11. So when we start working on it, we're going to have 9 times. We're going to have that formula. But instead of n, I'm going to write 11. So it'll be 11 squared times 11 plus 1 squared all over 4. And this gives us the very ridiculous 39,204. But if I add the first 11 cubes, I get 4,356. Okay. So this gets a little weird because now we have formulas that our sigma is written in terms of K, but the formula is also referencing N. For the purposes of the sigma, the N is a fixed constant. So we're going to factor it out just like a constant multiple. So my sigma can distribute across the subtraction, but I can pull out any of the non-K stuff. So the first half of this is going to be 5 over n squared times the sum from K equals 1 to n of K minus 8 over n times the sum from K equals 1 to n of, we factored everything out, so we need 1 as a placeholder. So on this one, I'll keep the 5 over n squared, but my K equals 1 to n sum of K, I'm just going to come over here and put in that formula. So this will be times n plus 1 over 2. Minus 8 over n times. So the sum from K equals 1 to n of the number 1. So we're just adding 1 a bunch of times. How many times do we add the 1? So which is it, K or n? Yep, n, because that's our endpoint. So we do this increment n times. So if it was from K equals 1 to 5, we do 1 plus 1 plus 1 plus 1 plus 1. 5 once. So we can have a crazy formula like this, end up getting rid of our sigma notation by using our knowledge of the way sigma works. The sum of a constant is n, the sum of K from 1 to n is n times n plus 1 all over 2. And if I simplify this all together and then take the limit as n goes to infinity, this will actually approach a constant. So now that we've had the whole segue about sigma, now how the heck do we use it for a Riemann sum? All right, so we're going to use delta x to be the width of the base. And we're going to force that to be the same width every time. Now, by forcing it to be the same width, then I just need to know my start and my endpoint interval numbers, which we often represent as A and B. So I figure out the distance between them, and I divide it by however many rectangles I'm doing. So in here, a lot of people just memorize that as a formula, which is not wrong. But it's coming from just equally subdividing an interval into n widths. Then we have f of x sub I with an asterisk. So here, this is whichever height we're going to pick. So it could be the left endpoint, it could be the right endpoint, it could be the midpoint. We'd figure out a formula for whichever x value we want and put it in there. Most of the time, though, we stick with the left endpoints because there's less thinking involved. All right, so fancy notation, but this introduces the Rn to be right endpoint approximation. So it's establishing a sequence of X numbers here, where X sub 0 is our starting value, X sub n is our ending value. And then there's a function value for each of the X's in there. We can do the same idea for the left endpoint. The big thing to note though is when we're doing the left, we're going to use X sub 0, and we're going to stop at X sub n minus 1. When we go back and look at the right one, we started with X sub 1, and we ended up using all the way to X sub n. But really, those are just two different ways to pick rectangles and add them all up. So with n equals 3, this is very clunky. So to make this area more accurate, if we subdivide it and make more rectangles, then the amount over or under we are gets smaller. But we have to do more work. So you can see there's a lot more error margin on the left than there is on the right. There is still some on the right, but it's not as big as it is on the left. Like fewer rectangles versus more rectangles. So now we finally put the calculus into this. So up until now, all of that was technically algebra. And that is why we used to cover sequences and series in pre-calculus, but we don't have the time. So we do it in here now. So if I take my number of rectangles and make it an infinite number, I take the limit as n goes to infinity of this Riemann sum formula, the left or the right endpoint. But that should actually give us the area under the curve. All right, so I'm going to start this, and then I'll probably record a video at home where I do the whole thing start to finish. All right, so here we are looking at f of x equals 7x squared plus 9. So that is a parabola over the interval 0 to 2. So let's So at x equals 0, it's going to go through the point 9. And then at 1, it'd be going through 16. And then at 2, 28 plus 9, 37. So it's going to go up a bunch. But that's just our basic like picture of what's going on. All right, they did tell us to use a right endpoint. All right, so I'm going to subdivide this into however many rectangles, but the width of each rectangle is going to be the same. So my number of rectangles is my arbitrary n. So our delta x is 2 minus 0 over n. So it is 2 over n. So each of our rectangles, if we were doing 4 rectangles, they'd be 2 over 4 units wide, a half a unit. If we're doing 10 rectangles, they'd be 2 over 10, which is 1/5, a fifth of a unit wide. If we're only doing 2 rectangles, 2 over 2 is 1. They'd be 1 unit wide. It'd be a very rough approximation, but it is still getting there. All right, so the whole x1, x2, x3, and then x sub k, this is figure out a formula for getting each of those endpoints. So each of the x values where we're going to want a function value, we want to come up with a way to generate that. So here my x sub 0 is 0. My x sub n is 2. So my x sub 1, like my first tick mark over, that's 1 width over, right? So my starting number is 0 plus my delta x times 1. To figure out my next one, well, I take my starting number, and now I'm going to add 2 widths. To get my third one, I'm going to add another, so I have delta x times 3. Okay. So I deliberately went to the effort to write the 1, 2, 3 because it correlates to the 1, 2, 3 that we're seeing on our x's here. So if I wanted to generalize this to k, I would still have my 0, which is my a value, the starting endpoint, plus my width times k for how many widths I'm looking at. Now, delta x, we actually have a formula for, though. So delta x is 2 over n times k, and I didn't write the 0 plus because it doesn't do anything. So this is a sequential formula that will give us all of the x values that we're going to use as endpoints for our rectangles. So the f of x sub k is take that formula, shove it into f. That gives us our heights. Then we do the height times the width. That'll give us another formula. Then we do the sigma notation, and then we finally do the limit, and that will actually answer the question, the area under the curve from the x-axis to the curve between 0 and 2. So I will finish that one in a video. But the starting part seems to be the more confusing than the ending part. Like the figuring out the delta x and then splitting the formula. I don't know. All of it's pretty convoluted though. But remember how we learned the long form of the derivative and then we learned the shortcut? This is the long form of the integral. But we hate this too, so I don't think we're putting a Riemann sum on the final. But it is in your homework. So we do want you guys to like get practice thinking about the area under the curve. But you're not going to have to like do the long way very long.
The final, is it just over the scenario of the accumulation?
It's a cumulative. So we're going to split the final. It's going to be like half and half. So it'll be half new stuff and half older stuff.
Not too early, but how long is it? Questions?
Oh, 8.
8 questions. Okay. So same format, 8. And we'll kind of go through that.
Yeah, it's just we have an hour and 50 minutes. So like we were doing 5 questions in 50 minutes. So double, like 8 questions. It's not quite double, but it is more than double time.
Okay.
So we felt that was reasonable.
When you do it?
Hmm?
When you bring it? It's Friday.
I think it's Friday. Yeah, like the Friday of finals week. Thanks, you too. Let me hit stop recording.